Okay, okay, good.
So maybe if you.
Okay. Okay, so thank you very much for the invitation, for organizing this seminar, for giving me the opportunity here. It's a pleasure to be in Portugal. It's the first time I'm in Portugal. Thank you, Dario, for this introduction. So I would like to tell you about a result that combines, if you want, geometry, more specifically the curved space-time geometry of a curved black hole with the statistical description of a gas, a collisionless gas that is propagating around this black hole. And most of the results I'm going to talk about in collaboration with my former PhD student, Paola Rioseco, who is now in the Universidad de Chile. So almost all I'm going to talk about has been done with her. So the outline of my talk, as Dario said, so I will first spend some time telling you or trying to motivate this mechanism, this damping mechanism which occurs in a collisionless kinetic gas. So that is something different from the Boltzmann H theorem. You might remember, which drives entropy, which through the entropy production drives the gas to a thermal equilibrium. So here we have no collisions in this model. So the entropy is exactly constant, but still there is some mechanism that leads the gas to equilibrium. Okay, so I'm going to motivate, so to start with a few systems where this is expected to be important or might be important. So, okay, then I'm going to describe, this is a battery, I think it's dying, but I'm going to describe to you this, what is mixing, or to define to you what this mixing is. And then at the end of the talk, then we will move towards Kerr, and I will tell you about a result we obtained recently for the dynamics. So this is about the dynamics of the collisionless gas around Kerr black hole. Okay, so first of all, so you might agree with me that one of the most fascinating topics in physics is the emergence of irreversible processes from fully reversible and microscopic laws. Okay, so as I said in this talk, I will describe to you such processes with a view to phase-space mixing, which I'm going to define later, and apply it to the class of gas and its black hole. And as a motivation, so let's look first at a few physical scenarios where phase-space mixing plays a prominent role. So the first example is something that has nothing to do with GR. I mean, it's even Newtonian examples. So it's what is known as Landau damping. So you have just a plasma in a box, which is modeled just by free electrons. No, they're not free electrons. They're electrons. They're interacting only through the Coulomb interaction. Okay, so the equation that models the system is the Vlasov equation, the collisionless Boltzmann equation. So F here is the distribution function for the electrons in phase space. Okay, so if you integrate the distribution function over P, you get the number density of the electrons. Okay, and the distribution function satisfies this equation, this Franz-Bold equation. And phi here, this is the electrostatic potential, which solves the Poisson equation. Okay, so Q is the charge of the electrons, if you want. And Ni here, that would be the constant, which, if you want, models the ion density, which I assume to be constant here. Okay, so this is a very simple system of equation. It looks simple, and it's actually fully reversible in time. So if you have a solution forward in time, you get also a solution backwards in time. It's time reversible, but still. So what you can prove here is that even though these equations are fully time reversible, we're not observe a relaxation. So if you ask, for example, So if you start with a homogeneous density for the electrons and perturb it a little bit, and now you ask what happens when T goes to infinity, then you can prove that this actually converges to something that is homogeneous. Okay, and this is in the linearized case, this was explained by Lambda some years ago, and recently this has been established in the nonlinear case by a famous work by Muo and Villani. And shortly after, Cedric Villani got the Fields Medal partly for this result also. So this was an important non-trivial theorem to prove, say. Okay, so you have this relaxation phenomena for the electron density. Now let's look at a completely different system, which is mathematically described by almost the same equation. So if you look at galactic dynamics, so a galaxy you can have the order of 10 to the 11 stars or something like this. So you can model this also as a kinetic gas. As in the previous case, it's almost collisionless unless you look at time scales, which are cosmological, but if you look at shorter time scales, then the probability that two stars collide is very low. So in first approximation, you can model this system. I mean, not as a kinetic gas, but now the molecules are the stars, if you want. So F now here is a distribution function of the stars, always the mass density. And now the only difference is that of course, the coupling constant has another sign. So it's attractive and repulsive plus C4. So you have the Poisson equations. Again, you have this Poisson equation you have to solve. And again, this is a fully time reversible system. Yet, one has some indication that in galaxies there is some kind of more or less universal distribution function. So when things that it's again converge to the staging state, of course, the staging state in this system you cannot put in a box anymore. So now you have its end state will now depend on X. So as far as I know, this is mathematically still not yet established, but Lynden-Bell 50 years ago, or 60 years ago, thought about this problem that motivated him. It's violent relaxation, which involves also this mixing mechanism. So astronomers think that this relaxation to a stationary configuration is also due to phase mixing in this problem. Now let me show you a related example. So these are some numerical simulations that Dario did with some collaborators in Mexico, Miguel Olivier, and some postdocs and students at that time. And what is shown here is the way what they did. They just looked at the toy model to stimulate the evolution of inhomogeneities in a dark matter halo. So they started to have an external Navajo-Frank-White potential. So this is again a Newtonian example. And then what I show you are snapshots at different times in their simulations. So this is R and PR. So this is the radial part of the phase space. So they start with some Gaussian initial configuration, and then they let it evolve. So later times you see it starts to do something, and then they observe that after a long time, it kind of relaxes to what they call a viralized state. So we'll come back to this example in a little while. Yes. Yes.
Here the particles feel these kind of external potential each other.
No, well, only through no. So this actually without the self-gravity. So this is just so they feel the external potential, but nothing else. So these are free particles. Yeah. So there's no interaction at all between the particles. Yeah. By the way, interrupt me. Feel free to interrupt me whenever you want. Yeah. Okay, and this is a problem I would like to solve, so that if you want the problem where you have a supermassive black hole, say you have an accretion disk around it, you have a jet and so on. And now, I mean, the system is described, I mean, if you want to describe through this kinetic theory, then you would have now the Boltzmann equation. So you might have collision between the particles, so you have a collision parallel Q, but now also you cannot do it anymore in the Newtonian regime, because if you're close to the black hole, the curvature is very strong, particles might be moving close to the speed of light, so you need to solve the relativistic Boltzmann equations, which look like this. And then also the particle could divide as a strong electromagnetic field, so they're coupled to mu. So this is coupled to the Maxwell equations, and then maybe even if the cell gravity becomes important, you might also the Einstein equations. So that if you want the full system for this problem, so here J mu is the current density, so it looks like this, the zero component you want that would be analogous to the particle density I showed you before. And T mu is a stress energy tensor. So, so note that you will have pressure and not dust, you will have still pressure because the spatial components of T are not necessarily zero when you integrate this. So you have this kinetic pressure in this problem. Now, well, let me make some advertisements. So we wrote several review papers, and so it is well established how this equation should look like. So the theory is well developed. So early work by Israel and Stewart and Ehlers and so on. And actually, if you like geometry, it's very interesting to study the geometry of the phase space. So this is you typically formulate it on a sub-manifold of the cotangent bundle. And then you have many interesting structure, like a metric on this cotangent bundle. You have a nice natural symplectic structure, and then you can formulate all this theory in a fully coherent form. And then you don't have to worry anymore if this is coherent or not. This is just building theory. So we wrote a few reviews about this. Then the other point I would like to say that to model this problem here, I mean, most of the investigation has been done using the hydrodynamic approximation, at least for the ions, maybe for the electrons now, people start to use kinetic models. On a fixed metric background, that's okay. If you have a supermassive black hole, then the gravity will be, the cell gravity is probably negligible, so then you don't have to solve Einstein's equations. Right, but with these full Boltzmann equations, so that's of course very difficult because it's an integral differential equations. Okay, so now in this talk, what I'm going to do is I'm going to simplify the problem enormously. So I'm going to cross out all the all these terms. So we are going to neglect collisions for this talk. We are going to neglect. We are going to assume there is just one species of particles and they don't interact electromagnetically either. Okay, so we just have to solve the collisionless Boltzmann equation, and then also we're going to assume that the cell gravity is negligible. That's probably okay. So basically, we just have to solve the vacuum Einstein equation, and if the black hole is in equilibrium, we have did that for us already. Okay, so this model is of course very idealized and is surely not going to describe what I put here in the picture, but it might still be relevant for, I don't know, for dark matter or distribution of stars outside the black hole, something like this. All right, so now let me define to you what this phase-space mixing is about. So, I mean, let's go back to something very fundamental. Let's assume we have a Hamiltonian system, autonomous Hamiltonian system in two-dimensional phase space. In statistical mechanics, as you remember, the passage from the microscopic world to the macroscopic world is done by origin. So more specifically, we have a deep cell zone, which is described by this density, the whole T. Okay, and then if you have an observable phase space, like the energy or angular momentum or whatever, okay, then you compute this macroscopic average at the time t is just the integral of phase space of this observable O times the Gibbs compound and the integral of phase space. Here I assume that it's always normalized. And then, because if you know the revealed flow, so if you know the Hamiltonian flow, then you know what's the time evolution of this Gibbs of this, so this is the inverse flow. And now the key question is that this object which depends on t, if that converges in time, or if it reaches equilibrium. Okay, so the key question is, is there like an equilibrium ensemble, let's see, which I call here rho infinity, so that this limit not only exists, but you can compute as the integral over the same observables times this rho infinity. Okay, and then you are in the realm of statistical of equilibrium statistical mechanics. Okay, and this should hold for all observables. Now, the first observation is that you cannot simply put the limit inside the integral. Okay, I mean, it's tempting to do so, but as we'll see, usually this rho doesn't converge, at least it doesn't converge pointwise. Okay, because typically, if you think about like a bound system, and the particle trajectory is typically they're like a quasi-periodic motion or something like this. So rho of t might not, so with this limit of rho of t for q and p fixed, that usually doesn't exist, and it will not exist actually in the problems I'm going to show to you. The other observation is that, well, as you know, this Hamiltonian flow leaves the energy invariant. Okay, so this is energy surfaces are invariant on the Hamiltonian flow. So if this rho infinity exists at all, it should depend at least on the energy. Okay, because of this problem. Okay, and now so here at the top I copied this question, so does there exist an equilibrium of sound? And now we're going to distinguish between two different types of mixing. So the first one is the strongest possible effects, which is called chaotic mixing. And this means that so we have chaotic mixing when this equilibrium function exists, and it depends only on the energy. Okay, and then you can actually compute this if you have your initial distribution function or your Gibbs ensemble, if you want. Then this comes out, you can show easily that this is just the average of the initial distribution function over the energy. So we divide by the volume of the energy. Okay. Okay, and this typically occurs when the system is chaotic, so it's sensitive to initial conditions. So that means, if you want, that's another way of stating this, that I mean, the trajectories that we visit almost all of the phase of this energy surface, and then this is what happens. And by the way, this is related to ergodicity. And if you want to know more about this, there's a very nice article, an old article, which is by Leibowitz and Olivier Penrose in Physics Today in 73, where they explain all these concepts in much more details in a nice acceptable way. And they make an analogy with Cuba Libre, which is a mixture of Coca-Cola and rum. So I invite you to look at this. Okay, so this chaotic mixing actually implies ergodicity. It's a stronger condition than ergodicity. Okay, what's going to be relevant for this talk is phase-space mixing. And phase-space mixing is if you have a Hamiltonian system which is integrable, or at least nearly integrable. So in this case, in addition to the energy, you have over a set of n conserved quantities, which are in evolution. So typically in classical mechanics, you have this invariant tori, where the motion is confined to. And then you say that you have phase-space mixing with this equilibrium function Z. And in this case, it is very easy to compute, to show that you can compute it by just taking the initial distribution function and you average over this invariant tori. So here J are the action variables, so the constant of motion if you want, and Whereas in the previous case, you reduce the number of degrees of freedom from 2n to 1. So you had a 2n-dimensional phase space, but at the end, the distribution function depends just on the energy. Here it's a dramatic, the reduction from 2n to n, but still it's a nice reduction of the numbers of degrees of freedom. Let me try to illustrate this in a very simple example, a toy model example, just in two-dimensional space. So let's start with the harmonic oscillator. That's unitary frequencies of is the Hamiltonian, the symplectic form. So here, I mean, we can introduce angle variables, so the angle variables which is the angle in phase space, and basically the action is that relate the energy, which will just be related to the radii of the energy surface, which are surface in this case. And then the equation of motion is so the q dot is just 1, that means the angle has constant velocity and the energy is constant. And then if you start with a distribution of particles, so in phase space, we have, let's say we take a Gaussian distribution function. Okay, and now what happens if you evolve this in time? This will just be a rigid rotation, right? Because the frequency is constant, so all the particles are just moving. After some time, pi, it will be on the other side, and so on. Yeah? So in this case, there's no mixing. Now let's modify this example slightly. So now we change the Hamiltonian to nonlinear function of x squared plus c squared. So f of e is our e plus the quadratic correction. A is a small parameter if you want. Okay. Now again, if you introduce angle variables, now h will be f of e. So if you compute now the q dots, which is the h by d, so this will be frequency function, but now you see the frequency function depends on the energy. So that means if A is positive, then particles with high energy, they will have larger angular momentum. So the energy is still conserved, of course. So you see what happens now is that if you start with this Gaussian distribution again, then it will look like this. Algodón de azúcar, ¿no? Sugar, so this will move faster. After some time, it will look like this, after like this, and then after if you wait for a long time, it will basically feel like a disk densely. And what does it mean? So if you measure now, for example, the density, so let's say we put an observer here at 0.3, and let's say we measure the particle density, so that means we integrate over the vertical axis, which is the momentum. In the first case, where there's no mixing, it will just fluctuate, right? It will go up like there will be a first peak when the central took out and cross the first time this red bar, and then we go down a little bit and we go up again when it crosses the second time, then it goes to 0, and then it will be perfectly periodic like this. Okay, however, in the other case, where there is mixing, then you see what happens is that it will basically, if you wait for a long time, it will basically average out and it will converge. So this integral over n will converge. And this is actually what to compute from a numerical simulation. So they oscillate, but these oscillations, they go down and they integrate for a long time, and you will find convergence to the value that you will find if you just smear out its emission. You can find it over there. If you just average it out. Okay, and this is basically this mixing effect in this two-dimensional setting. Now we can build like more realistic toy model problems. So now we can, instead of looking at this harmonic or reformed harmonic oscillator, just look at particles which are moving a potential well. Okay, so this is a potential well on my so the details here, but basically you have periodic orbits. Okay, and now you take again an ensemble, so many particles in phase space. So you solve again the Blasov equation. The Hamiltonian looks like this, and then you can actually prove the following results. So again, you take the distribution function. Let's say we multiply the test function. Okay, so the test function will tell you I'm probing like so some region of phase space. Okay, so I am saying the variable that depends on t, and now I can show that this n phi of t converges first of all. Now it converges to what you would obtain with the same integral if you replace f with its average over the energy surfaces. Okay, and there's a condition for it, like in the harmonic oscillator case, it didn't work. And the condition here that you have is mixing is that you should make sure that the period function, so the period function, the function of the energy, so its derivative should be almost everywhere different from zero. So if the period is constant over some interval, then in this interval you have like periodic motion, and then this mixing goes away. Okay, but if you have linear, so you can show that if this is different to this derivative and different from zero almost everywhere, then you can prove this this mixing result. Okay, so actually we applied this theorem to the simulation that the Rio and collaborators were doing. So this is the initial state and the final state, and you see if you draw here, they actually did that in the paper. So these are the energy curves in the model, and sure enough, what they find is that the end state is just the average of this initial state over the energy surface. So Paula wrote a code, a mathematical script, I think, which computed this average, and then we compared it with the final state. And sure, I mean, it agreed that it's qualitatively, I mean, they use finite volume methods, so that's some artificial dissipation in it, so it's qualitatively at least, it's agreed very well. Okay, so now let's go to. Yes?
I remember, yeah. The evolutions that we made, you have to evolve the rest of the equation, even in spherical symmetry is complicated, and it took around months or 2 months to arrive to them. Finally, they can, it was really a surprise that Olivier in a mathematical page of this thing, that was quite astonishing.
Okay. Let me surprise you.
Yeah.
Yes, good. Yeah. Okay, so this is still very simple because there is no self-gravity and so on. Yes, okay. Now, in the two-dimensional case, you can upgrade this theorem if you want to the two-dimensional case. So if you look, for example, at an axis-symmetric configuration with the central potential, right? So I of R, then you have this Hamiltonian, and then you can show again mixing, and this condition for mixing now is interesting. You can reformulate it in a nice geometric way. So in this case, what you have to look at is the area function. So the area function is you take an orbit of fixed energy and angular momentum, and you draw the orbits here in the phase space, in the radial part of the phase space of the Earth. And the area function is just the area under this curve. Okay, so you can show if you derive this area function with respect to the energy, you get the period in the radial motion. And remember that the curve derivative of this period has to be different from zero. So here, the condition to have mixing is to take the Hessian of this function for the second derivatives, and now the determinant should be zero for almost all orbits. And then you can show that there is mixing. Okay, if you have a three-dimensional system with its spatial symmetric, then you get, I mean, really this system has four integrals of motion in general, with the energy and the three components of angular momentum. So in this case, if this condition is satisfied, you still have mixing if you went in two directions, but not full three-dimensional mixing because you have spatial symmetry. So you have the so this is understood. So let me give you a very simple analytic example that you can find in the book by Bill and Tremaine. So this is this isochronic potential. which are this parameter B. So you see B is 0, then this is the Kepler potential. Okay, and then you have no mixing. This is of course related that the trajectories are closed orbits in this case. But the nice thing is that even if B is positive, you can compute this array function analytically. And this is the result. And now you see what happens. So in the Kepler limits, B is 0, then this is linear in L. So that means the Hessian has like a column or a row which is 0. Then this condition is not satisfied. But if B is different from 0, it is a non-linear function of L. So the Hessian will be diagonal, but diagonals will not be 0. So then there's mixing in 2 dimensions in these positive numbers. So this is the potential they use, I think, for star clusters. That's a toy model for star clusters and so on in this book. Okay, and then if you look at the Navajo-Frank White potential, that's the collaborator use. So this is the potential, and then you can look at this condition. We were able to compute it analytically, but graphically you can plot this determinant, and at least in this region you see it's different from 0, which justifies this mixing condition. Okay, now let me, before moving to Kerr, let me show you some first preliminary tests still for the Newtonian case, but where you include now self-gravity. And this is a code that Eric Jimenez, which was a former student of Miguel Alcubierre, he was my postdoc for some time, did. And now this is sort of what is shown, what is being done here. So this is now using this isochrone potential. However, now the gas particles that are put in when taking into account the self-gravity. Okay, and for this needs to be solved numerically. So Eric wrote from scratch the particle in cell simulation. And what is shown here is the initial state and the final state in this RPR diagram. So in the, yes?
So if particles see each other gravitationally, it's kind of an n-body system. So you don't have integrability, right?
That's right. Yes.
So you are taking kind of taking integrability and then making kind of adiabatic changes to the conserved quantities, because otherwise you don't have it would be a chaotic system, right?
That's a question to analyze. But so this is why the reason why this is so numerically. So yes. So we cannot solve this analytically anymore, and they're not exact in any way. I mean, you could, you should try to do it with perturbation theory, but still, because it's coupled with Poisson equation, there is an infinite-dimensional system, because the number n is typically very large, right? Yeah. That's right. So in this example, what I'm showing you, because you just see the initial phase and final phase, they look similar to what I showed you from this equation that I showed you. But this is a case where the mass of the gas is 0.1% of the mass that generates this external potential. So here you expect, of course, the cell gravity not to be involved, and sure enough, that's what is found here. So this diagram I showed you is the action angle variables. So they are now not really action angle variables, because as you point out, it's not integral, but you can still use them to parameterize space. And basically you see that its end state is practically independent on Q. So it just depends on K when you make the energy of each particle. So basically here, as you expect it, if the mass of the gas is small, then nothing dramatic happens, and then you find what you expected if you completely neglected the self-gravity. Now this is so we wanted to see how long does it work. So this is model where you have how long you have mixing, and here we increase the mass of the gas to 5%, like the mass of the initial of this external potential, and now you see it's much more complicated. Okay, so now you see, because now of the self-gravity, then of course now this central region has the inclination, say, to form like a compact object, if you want. Okay, that's what we see here. So the interior region has mixed. They're still mixing this exterior region, and this is again this action angle variables for the exterior potential. So you see here, it looks like similar to what you would expect if they're mixing, but here you see like more crowded things. Okay, so this mixing will compete, say, with the self-gravity of the system. No. So this is spherical symmetry. Yes, it is not only spherical symmetry, but it's even with a fixed angular momentum. So each particle has the same angular momentum. Yes. But you see, even in spherical symmetry, it's already a 2D problem. So that's why, I mean, people that are doing plasma physics, I think they claim that this is the best method, numerical method to solve them. So this particle in cell method. I think Alejandro Cruz is also using this. And he's doing it, I think, in 3 dimensions.
This is very effective.
Yes. So here we have, I think the most particle has used is about 1 million, and we were very proud of it. But then Alejandro Cruz told us he is using 10 to the 9 particles. Apparently, he used all the cluster for the channel as well. Yes. But yeah, so the problem with this method is very nice, but it's noisy also. So you have to be careful about convergence and so. Okay, so that was to give you an idea, say, of how, well, when is the self-gravity becoming important? And in the problem I'm going to switch now, so assume you have the Kerr black hole, which might be a supermassive black hole, and then we're going to look at a gas which might be just a few solar masses heavy. So then we learn from this example that we probably can neglect the self-gravity in a safe way. Okay, so now let's look at the Vlasov equation in the relativistic case. So I take the parametric that you know it very well. And well, the work we did with Paula, so we just went concentrated on this. Some of our results are valid in this part of the diagram, so it's an exterior region, and then inside the black hole, but not part of the Cauchy horizon. And then we start with Kerr-type coordinates to cover this region, and we assume sub-extremal black hole. Okay, so A squared is less than M squared. Also, the result that we're going to show you is about bound trajectories. So everything happens in this region here. So this region will not be important. However, some of the results are in preparation to look at the accretion problem. It will be interesting to see what happens across the horizon and maybe what happens when they reach a Cauchy horizon. Maybe a more academic problem, but still it's a theoretically important problem. Now, because the particles are not interacting, so no collisions, no self-gravity, so they just follow geodesics, and then the nice thing about the Kerr geodesics, they are described by an integral system, as Carter told us. And then you can generalize this notion of action angle variables in this context, and it had been done before in the literature, but we put it on a rigorous basis, and it involves a lot of nice geometry and theory of dynamical systems. So let me walk you quickly through this result. So the first of all, you have 4 constants of motion. So the first one is just the Hamiltonian, which is p squared, or 1/2 p squared. So these are related to the conservation of the mass. And F1 and F2 are the constants of motion associated to the one where you expect conservation of energy and estimate angular momentum. And then you have these Carter constants, which terms of phase-based variables like NP, you can write them this way here. And then the first thing you can check there is Poisson commutator. If you compute the Poisson commutator of these quantities, you can actually check that they're really zero. this contains in particular the statement that this F3 is a constant of motion. And then the second point you can prove is that you can show that these four quantities are really independent of each other. That means if you look, for example, at the gradients or the differential, they're really linearly dependent from each other, except at special orbits, which are typically like spherical orbits or controlled orbits. So those you have to take out the analysis, but they will appear like the boundary of the phase space. And these two statements together, they imply in classical mechanics that you have an integral Hamiltonian system. Precise statement. And then the next step, what you do, you look at the surfaces of constants equation, of constants, where it's quantity are constants, or where F0 is n squared half, F1 is E, F2 is LD, and F3 is F squared. And these two lemmas, they imply that except at these exception points, it is actually a nice four-dimensional submanifold of your phase space. So in classical mechanics, that would be the tori, typically, okay. And now, if you restrict this constant of motion to the one corresponding to bound orbits, I'm going to show you how to do this more in practice, then you can show that this set is actually has a topology R cross T3. Okay, so it's not compact because it contains a time dimension. Okay, so the time is still in here. So I have not introduced any foliation so far, so it's completely covariant so far. Okay, and now, so why is it T3? So where does this torus come from? So there's of course one cycle that comes just from the azimuthal coordinate, so pi goes from 0 to 2 pi. And there's another one that comes from the polar motion. And if you look at the polar motion, so this is characterized by this effective potential, so this is theta polar coordinate, and this is the effective potential. And interestingly, two things can happen. They can look like this, which is qualitatively like in Schwarzschild, or it can look like this, so you can have this minimum and this maximum. But for bound trajectories, you can eliminate, so you can discard this possibility. For bound trajectories, E squared is smaller than M squared, and then you're always in this case. Okay, so here you would have like periodic motion. And if you projected this on phase space, you would have like another circle. This is where the second circle comes in. And the third circle comes from the radial motion. And for the radial motion, you can write it in this way. So you have potential. So this is not unique. There are different ways of doing it. But one nice thing, you can introduce is shifted azimuthal quantity LZ hat, which is LZ minus AE. Okay, and now you have something that goes like E squared here, and then you can factor this, and then you get two effective potentials, W plus and W minus. And then what you can show is that if you want your particle to be future directed and not past directed, then you should go take the plus sign. Okay. This potential behaves qualitatively just exactly like in Schwarzschild. So it took us several months to prove it because it depends on a lot of parameters. It depends on the rotation parameter. It depends on LZ hats, on the Carter constant, and so on. So the analysis again actually proved that if the angular momentum for the Carter constant is low enough, then it will just be monotonously increasing. And then when it is above some critical value, then it looks either like this or like this. So there is potential well, and then you have this centrifugal barrier. And then here, of course, we will have another circle if you project this in plate plates. You have another periodic motion in the radial direction. Okay, so the only difference with Schwarzschild is that here, this potential or this minima and maxima will change according to the ratio between LT hat and L, which in the short case is like the inclination. So you can think of it like an analogous of inclination angle of the orbital plane. So here, of course, there is no orbital plane because it's not symmetric, but you can think that is an analogous quantity which gives you this inclination, and then this effective potential. The details will depend on this quantity as well. Okay, and then you can construct this generalized action angle variable. So you can almost use just standard theorems. So there's just one complication, as I mentioned before. This invariant set is not compact. And then you cannot use this famous Arnold Liouville theorem. But fortunately, this has been generalized to the case where this is not compact. And then basically the only thing that you have to check is that these vector fields, these Hamiltonian vector fields that are associated with conserved quantities that are complete. Okay, so that the integral curves can be continuous for infinite affine parameter, and this you can check. And then you construct these action variables in the standard way, more or less. So and there's a nice way of defining it, which is described in Arnold's book, Classical Mechanics. So the three of them you can define as topological invariants. So you take on the T3, on the torus, you take like the three cycles, okay? So the three curves which loop around each of these directions. And then you compute this integral of what is called a Poincare one form. So this is in our language P nu dx nu. And you can show, actually, you can prove that it's a topological invariance. So we can, if you deform the curve, this integral will not change. Okay. And then there's another curve where you cannot, yeah.
So what is exactly the meaning that the vector fields are complete?
Yeah, so does that mean that you can, if you look at the integral curves, then they exist for infinite values of the parameter in the past and in the future.
I see. Okay. So there is no place where there is there is no kind of singularity.
Exactly. And here we are safe because these are just down trajectories, so we're not hitting the ring singularity.
These are the given vector fields, not only because
yeah, exactly, good question. So
because one of those FAs is the one generated by the character.
Exactly.
Character constant. That's not the, well, it's a Kipling tensor. So in that case, what would be the XA? XA?
Yeah, so this is the, if you want the symmetry in phase space, advantage to this constant motion, but it has no interpretation on the side. Yeah. So and two of them are sitting in Killing field, and the other one is what is called the UV flow, because the Hamiltonian, one that generates Hamiltonian. Okay, and then the four action variables. So this needs to be associated to another curve which is not closed. Okay, and then there's no unique way of prescribing this. There's been different proposals in the literature, but we found that for our purpose it's very convenient to just do the math. Because then the Hamiltonian is just a function of unknown, and the UV flow looks very, very simple with this choice. Okay, and then the angle variables you can construct the generating function. And the generating function, basically, you go in one of these invariant sets, you will start with a fixed reference point. And if you give x, so you look at the fiber and you look where it intersects the fiber, and then you integrate now this Poincare one form over this curve here. So of course, it will depend on the winding and on other things. So it depends on the curve, so this has to be multi-valued. But if you compute it in this way, actually, you can show that you obtain, so Q0 basically will not be multi-valued, but the other ones will, but they have the correct periods, the period. Okay, and then, so at the end, what you get, if you want, you can, so this is the subset of the phase space corresponding to down trajectories. Then you have like the diffeomorphist, so the map, invertible smooth map that allows you to associate which point of the phase space for these four angle variables. So I mean, I really have three angle variables and one which is not an angle. And P0, P1, P2, P3, these are just a conserved quantities. Okay, so you should think of so this map, if you want, provides you new coordinates in the phase space, where you can think of Q0 if you want to parameterize this non-compact direction, and Q1, Q2, and Q3, you can think of angles around this toroid. Okay, and P0, P1, P2, P3, these are the constants of motion. Okay, so these are done. I mean, usually you put here the action variables, but we couldn't prove that the map from those to the action variables is globally invertible. So this we couldn't. It's more difficult to do in curve, but actually we don't need that, so we can just work with this coordinates. They're not exactly symplectic, but the symplectic form is simply enough so that we can solve, if you want, no problem analytically. Okay, and then so these angle variables, you can represent them explicitly in terms of Legendre analytic integrals, but I'm not bothering you to do exact expressions. But structurally, they look something like this. So there's some little QA which does not depend on T, and then minus omega AT. Okay, and this omega here, they depend just on the constants of motion. They are called the fundamental frequencies of the current motion. So once you have this variable, it's very easy to solve the sub-equation. The sub-equation basically tells you that the distribution function is the function of Q1, Q2, Q3, Q0, Q1, Q2. That's a solution. Okay, then you put any distribution function you like. And now we can look at mixing. So can I still have 5 minutes? Maybe yes. Okay. Thank you. So now, how do we parameterize the orbits? So in practice, it's done. So this is not something we invented. It's done by other papers. So typically, instead of giving the constants of motion, it's very convenient to work with the turning points that are already in motion, R1 and R2. And instead of the turning points, you can also introduce this fake if you want thing that is vector, but it's not. But you can still take just the Kepler formula and just transform R1 and R2 to P and E, where it is eccentricity, or like a fake eccentricity if you want. And beta is this ratio I mentioned before, which in the short debate will correspond to be related to the inclination angle. Okay, so this is the constant of motion. So we have instead of, so here I keep assuming that the mass of the part is fixed now. So then I just have these three parameters, P, E, and beta, to describe the orbits, where E varies between 0 and 1, beta between -1 and 1, and P is restricted at the lower limits, which is related to what is called the ice orbits. So in the Kepler case, P would be 0, but here in the black hole case, this is related to the maximum of the potential. Okay, and then the limits, you have all these interesting limits. So if E goes to 0, you have spherical orbits. If E goes to 1, you have these parabolic type orbits. Fairly monthly bound orbits are called times. If beta goes to plus or minus 1, you have equatorial orbits, depending on the sign that prograde or retrograde. These are called ESO, these are called the innermost stable orbits, and when P goes to infinity, then you have Keplerian orbits. And now it's very interesting. So if you compute this, so this is fundamental frequencies, you can compute them explicitly for any of the orbits, but you take the limit of circular orbits. So this is when E goes to 0 and you're in the quadratic plane. Then we call this these expressions here that are used of the people that are looking at the specific frequencies, so they match exactly of what on the literature. So I don't know what it is for, the first paper which traces this back to is the paper by Aliet and your friends, your advisor Gansov in 81. I don't know if there's been done before. And now the other interesting limit you can look at, and that's what we use to establish this mixing theorem, is to look at Keplerian orbits. So you look at orbits that are very far away. And then you can show that you have some analyticity in one of the square root of P. So you can make a systematic expansion in one of the square root of P. Some calculation takes some time, but let me just show you the result. So the Kepler limit, in the strict Kepler limits, then you know that this frequency are exactly equal when the orbit is in a plane where the orbits are closed. So this is an expression for the Kepler frequency. And then if you look at the frequency of the radial motion, you have some correction. So one correction was like 1 over P and 1 over P to the 3/2. Now, at the 1 over P correction, you see there is a break between the degeneracy between omega theta and omega r. Okay, and that means that the trajectory is not closed anymore. And actually, if you look at this expression, you can relate this exactly to coherent precession. So this is price exactly the coherent precession, then you have some other correction. And if you look at the next order, e to the 3/2, this is where the degeneracy between the two angular frequency breaks down. That means that the trajectory is not in a plane anymore. So you have this expression, and if you look at the books, this is exactly what is predicted by the Lex-Syrian precession theory. So basically what it means, you can think of it that every time the orbit crosses the equatorial plane, so this line between these two nodes is now precessing. It's precessing at least. Okay, and this is the result. So we derive this result, and then if you remember for the mixing, one should show that somehow the frequencies are independent of the constant of motion. That translates here that you should show that the Jacobian of the transformation from the constant of motion to the frequency has determined different from 0. So of course you say, okay, I know this frequency analytically, so I can analytically, yes, but still it's determinant is still a function of 3 variables. So how do I check this? Is it satisfied for our phase space? But using these expressions, you can compute this Jacobi matrix asymptotically and show that as long as the black hole is rotating, is satisfied with the determinant different from 0. Then you can combine this with an analyticity argument. So now we have an analytic function, one variable, and it is either 0 everywhere or a set of 0 or like a set of 0 of not 0. So it cannot be 0 in interval. So here you use a single argument, so you know if P is large enough, then this determinant is different from 0. Then that means it can have 0, but the 0 only a measure 0 set, and that's enough for mixing. Okay, so that's the final result for curve. So if you take a distribution function in some mathematical result, so that's putting some function phase and LP L1, 2, and then you take G would be the test function, okay? Then you compute now this observable, so we integrate L times G, basically. So that's, and then you can show that if the parabolic hole is rotating, then this limit exists, and it's given by the. Okay, so what does that mean physically? That means that basically the dependency of the distribution function, the angle variables, goes away, and you end up with a distribution that depends only on the constant of movement. You can observe and say that the stationary observer that she looks at the galaxy, she or he waits long enough that we just see well, the distribution that is that depends on the constant of motion. In particular, will mean that the end state is asymmetric or stationary, but also it has this carpet symmetry building. So it is invariant with respect to the symmetry we talked about before, with respect to the carpet flow. Okay, a corollary of this theorem is what is known as the physics literature, the Strong-Jeans theorem, which is something you put one hypothesis in, you assume the distribution function is just stationary, so you put one symmetry in, but you get three conditions for free. So just by requiring stationarity of the distribution function, this is enough to guarantee that the distribution function depends just on the constant of motion. So this is a direct consequence because if the distribution function is stationary, that means this is constant in time, and then f is equal to its angular rate. Okay, so this is something that has been shown not in the context of care, but in the Newtonian context by Jeans some time ago. Okay, so this is a result I want to talk to you about. So let me stop here. So the summary that you can read. So the important points that we use the problems basically from 6 dimensions to 3 dimensions. So 6 because we have 3 angle variables and 3 constants of motion, and now we will have motion. There are many open questions, interesting open questions. So what is the time scale and what this happens? Of course, obviously don't know very well yet. We are working on this. And then, of course, we see how self-gravity, collisions, or electromagnetic field is changing the picture. Okay, so thank you for your patience.
Thank you very much for the talk. So we had a few questions, but feel free to ask more. We have a little bit of time still.
I already asked, so well, I also already asked the question. But I will better. So, well, all of this framework is very interesting about. I think that it works for a case where you have an initial state that is already somewhere, like in the phase space, and you want to move, you know, and see how it works over time. But how about can this help us to say something about that case in which you have kind of an open system, let's say, where you can constantly inject particles, let's say you know the zero far away from the black hole, and you know what is the state.
Yeah, so for the Schwarzschild case, we looked at this. So this is an accretion problem. So you can imagine you have, for example, a reservoir infinity, and then you move. Like the Bondi mutual problem, and you send particles in, so temperature of infinity, say, and then so this is if you want the complement of this problem, then what you can show is that also so the reservoir gets the mass spatial infinity, then independent of the initial data. If you wait long enough, it will go to a stationary state, and then you can compute the accretion rate and things like that. For care, we are trying to compute this with Patrick Mark, and it's quite difficult. So we haven't made a lot of progress yet. There's like a paper that's published some results that we think they are wrong. Yes, but yes. So as long as you have no interaction between the particles, and you can separate it from confusion, either you have this bound trajectories or these unbound trajectories. So the unbound trajectory will describe accretion, and this describe this subject to mixing. This will settle down to this stationary asymmetric configuration. I think what's very interesting, if you now put in a little bit of collisions between the particles, like at the relative level or something, and now these two can interact, and then probably this disk that we get at the end will start evaporating, or it will start accreting. something we study.
Someone treated the problem of even just let's say aspect into statement, but with some angular momentum.
So what we did with Paula in the Schwarzschild case, so the particles can have angular momentum, but we looked, so we looked at so there was no total angular momentum.
Let's say
so the gas is not rotating inside. So the answer is no in this sense. What has been done is the wind scenario by Patrick Martin collaborators. So they looked what happens with Bonnie Royal, analogs of it. So this has been done for the short.
Thank you.
No, thank you.
Thank you very much. I enjoyed the presentation a lot. I have perhaps a couple of questions. One of them is perhaps, let's start with a fairly naive one. So, since these are constituted by particles that don't see each other, so how can you kind of relate this with the motion of geodesic? So, can each individual motion of the particle be described by a geodesic, or
that's right?
Okay.
Yeah, exactly. Yes.
Okay. So the other question is there, I think this kind of looks at the dynamics of the gas in the background of is there any, I was wondering if there is some kind of signature of integrability that can be looked at the pattern of motion of the gas. Because I was wondering if instead of curve, if you have something else, some kind of black hole geometry that is not curved, more often than not, probably you get something that is not integral. So you get some, instead of this phase mixing, you get a chaotic. Even if the particles don't see each other. So yeah, I was wondering if you thought about this, and if you have any comments to elaborate on this point.
No, that's a very good comment, I think. Yes. So indeed, if it's not fully integrable, then you will lose this alpha constant. And then it might or might not happen. That's the final distribution function might depend on even less. It might just depend on the energy and the azimuth. But I don't know. It would be nice maybe to have a model problem first, where this is easier to study. But you're absolutely right. Yes, that would be interesting, and in fact, it will be beneficial in some sense because this chaotic mixing is like stronger than this phase-based mixing. So on the other hand, then I mean people that sometimes use these CAM theory arguments to show when if it's a sufficiently small perturbation of this integrable system, you expect that you still have this deformed invariant tori, and then it might still be enough to get mixing. So
it would be a small perturbation of the curve.
Yeah,
that might not be the case.
But if it's not a small perturbation, then it's certainly complicated. Yeah, good comments.
Well, are there any questions on Zoom? I don't know. So if not, I suggest that we stop here. If you have more questions, of course, feel free to attend to Olivier, who will be there also this afternoon, and we can go further. So thank you again.